Cool, let's make a start. And yeah, welcome back. And now we have a talk by Jacob Pate, who is a lecturer at the University of Edinburgh. And lecturer is the funny British way to mean assistant professor. And he's gonna talk about machine learning for the dynamical systems approach to turbulence. Jacob, over to you.
Thank you, Luca, and thank you very much for the invitation. It's really nice to be back in Cambridge. I left in the middle of the pandemic, and it's nice to see the department with people in again. So I'm going to tell you about something that I've been working on really since I was a postdoc, which is what we call the dynamical systems approach to turbulence. This is quite an old idea, going back to Hopf, with, I guess, some real exciting progress in the early 2000s, and then it's kind of hit a roadblock. And so what I want to do is really tell you about why I think some of these ideas from deep learning are going to enable us to break through that barrier. So I'm going to focus on a couple of things. One is going to be a very simple problem involving convolutional neural networks. The most of my talk will be about this thing here, where I'm going to write down loss functions that are going to target particular exact solutions of the Navier-Stokes equations that I'm interested in. But the key thing is here that my numerical solver will be fully differentiable. So it's going to be written in JAX in this case, so I can just differentiate through entire solution trajectories and target solutions with particular physical properties. And I'll hopefully try and explain why that's useful and important as we go on.
Your numerical solver is not physics?
It is. The numerical solver is straight Navier-Stokes. It's plus physics. Okay, yes. Well, no, I can talk a bit more about what this bit does. Because if I just did gradient descent on this thing, it wouldn't necessarily give me an exact periodic solution with properties that I'm interested in. So this is more like give me something with particular physical properties. So in this dynamical systems approach to turbulence, what we would do is we would take, say, our computation, maybe resolve it on a very large number of grid points, and I'm going to think about that as a very large dynamical system. And then my turbulence in this dynamical system, any particular realization of that would be one of these long orbits, this orbit through the phase space of possible solutions. And it looks like this big kind of chaotic mess, this blue line here. But the useful thing about thinking in this way is that we can start looking for what are called simple invariant solutions of the governing equations. So these might be things like periodic orbits, simple equilibria, which are just fixed points in this state space. And then we think of our turbulence as being like a pinball bouncing between these objects. And the reason the objects themselves are really nice, well, there's a few reasons. One is their kind of encapsulation of key physical processes. So if you're interested in self-sustaining mechanisms, you might want to find these things. And I think one of the kind of early pieces of progress, this is from 2004, that got everyone very excited about these ideas, was this joint numerical and experimental paper led by Bjorn Hoff, I think when he was a postdoc. And what you're looking at here in the top right, along the top, are 3 snapshots from an experiment in a transitional pipe flow. So there's a turbulent slug propagating down this pipe. And what Bjorn is showing us in these pictures is we're looking down the pipe, and the colors are contours of the streamwise velocity. And so these are 3 snapshots from his experiment. And then underneath, you're looking at the same thing, but for 3 exact traveling wave solutions of a Navier-Stokes equations at that Reynolds number. So these are unstable traveling waves. They're exact solutions of the governing equations. And hopefully you don't have to squint too hard to argue that what you see on the top doesn't look dissimilar to these exact traveling waves. And so we have this kind of understanding of this transitional pipe flow in terms of this small set of exact coherent structures. And this thing here is basically bounced away from these things on their unstable manifolds and then attracted in on the stable manifolds of the others. I mean, I think the next result that really, and so I should say that was traveling waves. I'm mainly going to be talking about periodic orbits, which are these closed loops in the phase space. And the reason for thinking about periodic orbits is that they have a time dependence, right? So they capture some closed cycle of dynamical processes. And so if I am starting to think about trying to understand the mechanics of wall-bounded turbulence, for example, these things may be of use. So the point at which the community really started getting excited about these objects, these periodic orbits, I think was in 2001 when Kawahara and Kida converged the first periodic solution of the Navier-Stokes equations in a turbulent flow in inverted commas. So this is a minimal flow unit in a Couette flow. And what I'm showing you here is a picture from their paper. This is energy production rate and energy dissipation rate here. The big green cloud is a very long turbulent calculation. And then the periodic solution they found, the first ever unstable periodic orbit in the turbulent flow, is this closed red curve sitting on top. And the key thing in this projection is it sits bang in the middle of the green cloud. And if I show you a video of the solution, if you've ever watched a video of a minimal flow unit, and when I showed you this video, you're looking down between these plates at a plane midway between them, and this is streamwise velocity. If you were to watch a clip from this video and then watch a clip from the turbulence, you probably wouldn't be able to distinguish them. So this periodic orbit is somehow capturing this streak regeneration process that you get in this minimal flow unit. And if I was to go further and show you statistics of this periodic orbit and put them next to the statistics of the full turbulence, if you didn't know the problem very well, it would be hard for you to say which one was the periodic orbit and which one was the turbulence.
That's Ari tau.
Ari tau in this case, no, this is Reynolds number based on the half height, and the Ari tau in this case is very small. Yeah, so I'll get to this, right? So what dynamical systems people call turbulence versus what you might say is turbulent is quite different. Okay, and this is really where this whole field kind of gets stuck, because there was this great excitement that we have these objects in low Reynolds number. The next slide will appear at some point. At least I can see it here. So we have these solutions at low Reynolds number, and they have all these nice properties, and we can start to understand something about this kind of system in terms of these solutions. But as soon as we try and go to any realistic Reynolds number, all our methods fail. I don't know how long the delay actually is, but yeah, I mean, it's worked so far. I think the same thing happened in Petros.
Try to escape.
I still have a. Okay. Okay. This is my slide.
Oh, right.
There you go.
Okay. Yeah. Great. Thank you.
All right. You're going to have to watch in. Yeah. Okay. So now we are where I am here. So this has kind of been the roadblock, right? In these ideas, they had a lot of promise, and then what is the challenge? Why can't we do this in real turbulence? Well, I think the biggest issue is that the actual problem of finding and converging solutions at high Reynolds number. So there was a meeting here last year, and some of these ideas were talked about, and this really is the kind of leading order problem. How do I actually generate good guesses for exact periodic solutions that are relevant to the full turbulent state, and how do I converge them? And really, since the kind of early 2000s, the methods haven't changed a lot, and we're kind of basically not much further than where we were. The other thing is, if you have a set of these solutions, one other useful thing you might want to do with them is actually use them to do some prediction. And there's a very nice result from dynamical systems from Predrag Cvitanovic that basically tells you that in a hyperbolic dynamical system, if you have lots of periodic orbits and lots in inverted commas, then you can compute any statistic of those periodic orbits. So let's say gamma is some statistic. This could be a PDF of dissipation. It could be the mean profile, for example. And periodic orbit theory tells you that if you take all these statistics for the periodic orbits and you weight them in some way and you sum them up, then you actually get a prediction for that statistic for the chaotic attractor. And the key thing is here in this expression is that these weights do not change between statistics. So once you know these statistics for the periodic orbit theory, for the periodic orbits, you compute the weights, and those weights are then fixed across all statistics. So your periodic orbits, in some sense, give you everything. And so this is the kind of great promise in turbulence, is that we would like something like this. Get a set of these solutions, and each one of them is perfectly periodic. It tells you something about these closed cycles of physical processes, but it also tells you the role that these things play in the statistics of the flow. And that really, I think, is why I personally am quite excited about these ideas, although, of course, we're still stuck at this stage at this moment. And so I'm going to introduce a flow that I'm going to talk a lot about today. I'm going to talk about an even simpler problem at one point in this as well. But this really has been the testing ground for these ideas for a very long time. And this is Kolmogorov flow. So it's doubly periodic on a domain which is 2 pi by 2 pi. We have monochromatic forcing in the streamwise momentum equation. So this is just a sinusoid with a wave number of 4, and it's 4 just for historical reasons. And this here, this has a Reynolds number of 40, where the Reynolds number is based on the strength of the forcing. And you can see this thing spin up from rest, and it lands on this kind of chaotic, spatiotemporally chaotic system. If I was to show you higher Reynolds numbers, this gets a little more exciting, and we will look at higher Reynolds numbers. This flow has a number of symmetries. The key one for us in this talk is that there is a continuous symmetry in the streamwise direction. So I can take any snapshot of my equations, arbitrarily shift it in x, and let my solver run off again, and it's quite happy with that. Okay, so it's equivariant under shifts in the x direction. And we're actually not going to try and do anything explicitly about this symmetry. We're going to use this symmetry to understand something about some of the representations we get when we start using neural networks. So this is the old way of finding periodic orbits. So if you kind of believe enough of what I've said to think that it's useful to find them, this is what you would have done until this point. You're looking for exact periodic solutions of the governing equations. You store a very long time series from your calculation, and then you go to a time little t in the flow in your database, and you look back in history, a time capital T in the past, and you ask, was there a time in the recent history where the flow looked roughly similar to how it does now? And if yes, then that's a good starting point for a guess for a periodic orbit. Now that similarity between past and current time is done with just a simple L2 norm on the vector you get out of your computation. And of course, if we do have a symmetry like this continuous symmetry in X, we'd also have to search over shifts in that direction to find relative periodic solutions. And so you're looking here at contours of this quantity for this Kolmogorov flow. And basically, wherever this quantity is dropping below a threshold, some threshold here which is a relative error of 0.3, then what I'm trying to imagine has happened is that there was a perfectly periodic, it's closed loop in the state space. The turbulence has come down and shadowed that periodic orbit. So it's sat near it for a full period. It's flagged up as a near occurrence in this, and then the turbulence flies off. But I have my guess for this periodic solution. So there are a couple of downsides with this, with this approach. The first one, and I think this is really a key reason, the reason we've really been restricted to low Reynolds numbers for a long time, is it requires this near occurrence to occur, right? So we actually need the turbulence to come and sit near one of these periodic orbits for a full cycle before it leaves. And as you increase the Reynolds number, the periodic orbits typically become more and more unstable, and the likelihood of actually sitting in the vicinity of one of these things for a full period drops. The other thing is, this distance metric is L2 on the vector you're getting out of your calculation, and unless you have a very near pass, that's probably not a good measure for closeness on the solution manifold. So it's the second one of these that I'll kind of deal with first in this talk, and then I'm going to come back and try and remove the idea of, or this need for a near occurrence. So this is kind of state of the art in the Kolmogorov flow, and it hasn't changed in the last 10 years. So this is a paper that Rich Kurzweil did with his postdoc Gary Chandler, and this is kind of the benchmark that we're going to compare against. So, how is that approach done, this near occurrence approach done in the past? Well, at a Reynolds number of 40, they were able to get something like 50 periodic orbits. They were all low dissipation. When they pushed up to Reynolds 100, which starts to look a bit more exciting, they have, I think, 9 periodic orbits. They had enough periodic orbits at a Reynolds number of 40 to try and start doing this periodic orbit theory idea and make some predictions for the statistics. So you can see how they do here. These are 2 PDFs. This is the kinetic energy. This is the dissipation rate. The curves to look at are the blue, which is kind of your ground truth from a DNS, and then the pink, which is this periodic orbit theory. And you can see in both cases, the periodic orbit theory is failing pretty miserably. In this, if we look at dissipation PDF, we just don't have anything in the high dissipation tail. These are all these kind of low dissipation structures. There are also some control cases in the background. So I think this red curve is the case where they don't do anything. They just have uniform weights across the periodic orbits. And you can see that it does perhaps a little better than the periodic orbit theory itself. So that's the kind of state of the art, or at least it was about 10 years ago.
Yeah. How do you find the weights that you need to reconstruct, you know.
So if you actually do periodic orbit theory, and those weights depend in a kind of complicated way on all the flow K multipliers for the periodic orbits. There is a formula that you can write down, given the periodic orbit, how to compute these things. I'm going to do it in a data-driven way at some point. So this is a little more on those early results. I'm showing you some of the short periodic orbits that were found in that paper, and I'm showing you them in a couple of ways. So the period is on the x-axis of this figure, their dissipation rate is on the y-axis, and then I'm also showing you the dissipation rate against the production rate. The turbulent PDF is shown here, it's a big grey cloud, and these 4 short period solutions that Rich and his postdoc found are shown as little curves on top. Now, if you know periodic orbit theory, you'll know there's a lot of importance put into these things called prime cycles, which tend to be the shorter periodic orbits. They somehow capture their prime because they are kind of fundamental building blocks for more complicated dynamics. But if you look at these short periodic orbits in this system, they don't really give you anything in terms of the global statistics of the flow. And so this has led some people to conjecture that, look, we need the long periodic orbits in turbulence. This is spatiotemporal chaos. Maybe none of these ideas are relevant. We're going to need much longer ones. Or maybe if I'm interested in high dissipation, I'm going to need to think about more complicated simple invariant sets, like heteroclinic connections between these periodic solutions. So these are things that people have suggested, and I'll revisit these ideas a bit later in the talk.
I'm sorry, maybe I missed it, but how do you quantify production and dissipation? What are the quantities? Entropy and something?
I mean, dissipation is just the volume integral of the. If I look at the kinetic energy equation for the fluctuations, compute the dissipation rate on the right-hand side, so it's 1 over the Reynolds integral of the square of the.
Is it not the entropy?
It's in the 2D flow. It's exactly the entropy. So in this flow is the entropy.
So this is the 2D flow.
Yes.
And the production?
The production is just, your kind of typical Reynolds stress type term, so mean shear, average of the velocity fluctuations UV. So yeah, there's nothing, these are kind of the typical things you would compute in a turbulent flow with a one-dimensional mean profile. Okay, so the first thing I'm going to do is I'm going to try and do recurrent flow analysis again. But rather than using a distance metric based on physical space, on this computational vector, I'm going to create a new distance measure using a neural network. Actually going to build the neural network for a much simpler problem and then just find that it's very good at this recurrent flow analysis. But then what I want to do is really get away from the idea of measuring near occurrence altogether. So I'm at this point going to go to a much simpler problem, which I'm going to use automatic differentiation to find exact solutions in before coming back to this turbulent Kolmogorov flow at much higher Reynolds numbers and try and show you that we don't need to have near occurrence at all. So this first thing I'm going to talk about is work I actually started when I was a fellow here with Rich and also with Michael Brenner, who was, I think, at the time just come back from sabbatical at Google, and he came back very excited about what machine learning could do, and we talked to him about this problem, and so it was a natural starting place. There's some extra work at the end which also involves a PhD student, Joe, here, that I'll talk about very briefly. So I'm going to, I wasn't here yesterday, so I don't know what was said about autoencoders versus PCA, but I'm going to use a full nonlinear autoencoder, and initially the reason we were doing this was just as a kind of warm-up problem. We weren't necessarily thinking this would have any role to play in the hunt for these exact solutions of the governing equations. It turns out it's going to be very useful. So I'm going to have a big convolutional neural network, which is going to see snapshots of the vorticity field. So this is a 2D problem. So this is just essentially you can think of it as a grayscale image. It's 128 by 128 pixels. And I'm going to push it through a convolutional neural network where it's going to have this kind of hourglass-like structure. I'm going to reduce the dimension down to something small, less than 128. And then I'm going to take that embedding and push it through this kind of upsampling set of convolutional layers to try and get back something that looks as close as possible to the input. So initially, this very basic architecture, there's something like 4 or 5 convolutional layers in each of these with max pooling, few fully connected layers in the middle, and then I reshape that back out. And the whole thing is trained just on L2 of this, the output of the autoencoder, minus the input. So this is just an identity function, right? And if I was to, like Petros said earlier, if I make this a kind of simple linear model, I'm just doing PCA, but this is nonlinear PCA. And so, although I'm not showing you, how that thing performs, it does pretty well. I'll come back to the performance a bit later, actually. So we have these very effective embeddings of our turbulence, and I want to try and understand something about what the neural network has learned. And so I'm going to introduce something that we call latent Fourier analysis, which is a way we think of kind of interpreting what the learned representations, and it's going to exploit the fact that we have a continuous translational symmetry in the system. So what I'm going to do is I'm going to take the embedding of a vorticity field, so this will just be a vector of, say, 128 numbers. I'm going to compute the embedding of the exact same field, but the field now shifted by some amount alpha in the x direction, and then I'm going to look for a linear operator to do that in the embedding space. So I take my field outside the network, I take a shift to copy, I embed both of them, and then essentially I do DMD to find this linear operator for some shift that I design. And then I can figure out what the eigenvalues of this thing are going to be. They're just going to be the nth roots of unity, and I'm going to think about the number L that appears in the eigenvalue here as being what we would call a latent wave number. And so numerically this would be equivalent to doing a Fourier transform in space with some Nyquist cutoff set by the shift alpha that was your design. So why is this useful? Well, I can take individual eigenvectors of this operator and I can decode them, and they look like things that I'm interested in. So I'm going to try and show you that here. So what I'm doing is, on the left, I'm showing you the eigenvalue spectrum from my operator that I built from DMD in the latent space for some small shift alpha. And you can see that these latent wave numbers, they're going down here. So this is imaginary part of the eigenvalue. This is the real part. They all basically sit on the imaginary axis. And so we have these kind of real latent wave numbers. And I guess the first thing you might notice is that they stop at 3. So if I do a Fourier transform in physical space, I find energy in all my wave numbers decaying at some rate in the high wave numbers. Inside the autoencoder, I find everything stops at a latent wave number of 3. So the autoencoder has somehow learned a representation of the turbulence in terms of patterns that are at most triply periodic in the domain.
Should you not get the same thing if you do a Fourier analysis of the original signal?
No, if you did a Fourier analysis of the original signal, you would get energy right in all the wave numbers up to your.
But you can keep some of them, and some of them should.
You could, okay. So you could truncate that way if you want, and say I'm going to build a model based on the first 3 Fourier modes. But I mean, what do they look like? I mean, they are. I mean, you get the same thing, right? If you did PCA just on your input data, you would find you just get Fourier modes. And you could terminate at 3 if you want and try and build a model with that. But what I'm trying to show here is that this termination at 3 here somehow is capturing all the patterns that you see. So what I'm doing is, and you'll see actually that these, so maybe this is the difference. These are highly degenerate. So each of these eigenspaces is high dimensional, right? So a latent wave number of 1, there are maybe 10 important directions in there. And what I can do is I can take a snapshot, so this would be a true snapshot of my turbulence. I can embed it in my autoencoder, and then I can just project that embedding onto these different eigenspaces. So if I was to do this on the regular Fourier modes, I take a snapshot, I project it onto Fourier mode 1, and I just get a sine wave with some amplitude. But here I take the snapshot, I embed it, I project it onto a latent wave number of 1, I then put it through the decoder, and I get something that in the low dissipation snapshots essentially looks like what I put in. I get something that is periodic over 2 pi, but it has, if I did a Fourier decomposition of this, it has energy in higher wave numbers. It's somehow a fundamental pattern with a periodicity set by this latent wave number. If I decode the latent wave number of 2, if I was just doing this in physical space, it'd be a sine wave with 2 waves inside the domain. Here, it's a pattern which is doubly periodic in the domain, which somehow retains some of the features in the original snapshot. Okay? But of course, I mean, the reason these things are so rich, if I was doing this in physical space here, you just see the same sine wave again and again. There's this kind of rich variety of patterns here. And that's possible because of the degeneracy of these eigenvalue, these eigenspaces.
Is there any relationship between small and block block wave structures?
Like if I was, I don't think so. No, like if I was asking it to do something involving stability, maybe I did it for the linearized answer, maybe. But then if you, so now we have these high dimensional eigenspaces, and I want to actually pull those apart, right? So what I'm doing here is I'm taking my eigenvalues, my eigenspace associated with the latent wave number of 0, which is just the horizontal average, and the latent wave number of 1. And all I'm doing is then inside that eigenspace, I'm doing PCA. And then I'm taking the most high energy mode in that eigenspace and decoding it. And so you're looking at, on the bottom here, the decode of this pair of latent Fourier modes. Along the top, I'm showing you a true equilibrium solution of an Navier-Stokes equation. This is the first non-trivial equilibrium solution in the Kolmogorov flow that bifurcates off the laminar solution. It bifurcates off at a Reynolds number of about 10. And then here it comes. It becomes unstable quite quickly, but you still see the signature of it in your turbulence if you squint. But we never showed this solution directly to our autoencoder. But this kind of approach is telling us that this is basically the fundamental pattern around which everything else is built inside the autoencoder. So with just a pair of latent Fourier modes, I can reconstruct this exact solution all the way along its solution curve. Now this network was trained at 1 Reynolds number, and it was never shown this snapshot. But it's still learned that basically this structure is the best way to kind of build out a representation of the turbulence. So I should be clear, what am I doing in this bottom set of pictures? I'm projecting onto these 2 Fourier modes. I mean, all I'm doing is changing the amplitude in this inside my embedding of this first Fourier mode, and I'm able to then kind of faithfully reproduce this structure for a range of Reynolds numbers. So we thought that was pretty exciting because, yes.
Have you tried doing PCA directly on the embedding without doing the Fourier mode?
Yes, yeah.
And then the code goes direct.
If you do PCA directly on the embedding, you see everything's dominated by essentially a giant ring, which is the continuous translational symmetry. So you can do this, but you still have this issue that there's that continuous symmetry in there, and actually you have to project it out somehow.
Because I work on the same flow for a different Reynolds number, and I get something very similar. The code is directly there.
Okay. Yeah, I mean it's possible, right? If you I don't doubt it. But we have this. I mean, certainly when I look at the latent wave numbers higher than 1, well, they're useful for other reasons. Okay, so this is so basically what I can do now is I can take a huge set of snapshots, embed them, and build a shift invariant observable. So if I project onto my latent Fourier modes, take the absolute value, and then have something that I can observe in the latent space, which is invariant under shifts through the domain. And you're looking basically at a clustering algorithm applied to that data set. And there are a couple of things here. The first thing is you'll notice there's this kind of giant blue cloud here. The color here of these points is set by the dissipation rate. So this is all our low dissipation data, and it's arranged in a kind of octagonal structure. Why would we expect an octagon? Well, this flow has a shift reflect symmetry in Y. Basically means if I apply H shift reflects, I get back to where I started with, and so we can see that in this low dissipation dynamics. And then we have this little high dissipation cluster up here, where basically everything else is. So these are these kind of bursting events. And if I was to, I mean, essentially, I'll show you something else in a second, but all of these are very closely related to that first equilibrium that bifurcates off the laminar state. The bursting dynamics are controlled by other latent Fourier modes.
So this is very nice, very insightful how you explain it. The only thing that is non-ideal is you're enforcing the volume force, right?
Mm-hmm.
So how far away do you think we are from doing something like this for training or for the same
But we're starting now, right? So I mean, in terms of, I mean, that if you look at channel, yeah, okay, there's no body force, but there's still a continuous symmetry. So in theory, you could apply these ideas.
Yeah, I'm saying we can apply. It's just a matter of scale and a few other things. Right?
Yes. Yeah.
Very interesting. Most interested in seeing without external force.
Yes, yeah, and so it's a big limitation of this. But I mean, hopefully, maybe in a year or two, I'll say something about quite a slightly less idealized situation. So the last thing I want to do with that architecture is basically go back and do this recurrent flow analysis again. So this is this idea of looking for these exact periodic solutions. This is the old approach, right? You take the output of your computation and you look where you have these near occurrences measured with an L2 norm in physical space. And on this top figure, I'm basically showing you in green where I found solutions with this approach. Underneath, I'm doing exactly the same thing, but now I'm using a projection onto these latent Fourier modes to measure similarity between current time and the past time. The key thing here is that all these green squares, well, they are solutions that we then converged, and there's a lot more green squares down here than up here. And I've just highlighted in orange points where the previous analysis showed no indication of a near occurrence, but this new approach flagged a near occurrence and gave us a new solution. I think I probably, in the interest of time, should skip ahead. Maybe I'll say one or two things about this. So what this kind of projection tells you is that, for most of the time, if I look at a long time series and I'm looking at the dissipation rate as a function of time, I tend to hover around this low value, and every now and then you get this spike, which we would call a bursting event. And so this gray region here is highlighted here. This is a high dissipation burst. We can look at that in terms of our latent Fourier projections. Now, the thick blue line here is basically the projection onto that dominant latent Fourier mode, which was this first non-trivial bifurcation. And in the low dissipation regions, this structure dominates, right? Most of the embedding is built around that structure. When you have a burst, this thing just drops. Okay, so that structure is not important, and the burst is actually represented in terms of modes which are doubly periodic in the domain. So these latent Fourier modes with an L equals 2. And it turns out that we can actually, we have this understanding of what the L equal 1 mode is doing. Now, if I take one of these bursting events, I project onto this L equals 2 latent Fourier mode and plug it into my Newton solve, then I converge entirely new bursting solutions, which we didn't have access to. So these higher order latent Fourier modes have some physical significance as well. The old architecture basically has some limitations that I wasn't terribly happy about, that we've resolved very recently. But I think I definitely spent too long on this, so I'm going to skip ahead. There's a new architecture; it works much better. Happy to kind of talk about that maybe afterwards. But I really want to move on and talk about automatic differentiation. And so this is work with a PhD student in Edinburgh. I'm going to go and do a much simpler problem, which is the problem of finding vortex crystals, and it's really going to be a testing ground for some ideas. Basically, I want to apply automatic differentiation to look for exact solutions, but I also want to use these ideas to find more complicated simple invariant solutions. So, for example, if I want to find a connection between two exact solutions, then the old methods basically don't give me a mechanism for doing that, whereas automatic differentiation does. And so we're looking at this configuration, which is basically, it's motivated by what you see in a superfluid. As you cool it inside a rotating cylinder, you do not get a solid body rotation. Instead, you get these quantized vortex lines. But I don't really know a lot about superfluids. This problem is essentially point vortex dynamics, right? So rotating disk, there are point vortices in here. Their velocity is basically the induced velocity from all the other vortices, plus the images, and then we're also in a frame rotating with the disk. And the solutions that you observe in a real superfluid minimize the free energy. So if you actually configure one of these experiments and run it for a long time, you will see the lowest free energy vortex crystal emerge after a sequence of transients. The reason that for doing this is kind of a nice starter problem for a PhD student. There was a kind of open problem posed in this review from Paul Newton, where he said, oh, it'd be nice if we could get the energy minimizers in this flow for large numbers of vortices. And really, it's kind of an interesting community in that these ideas in dynamical systems have kind of flourished without moving over to people who worry about point vortices. And so there aren't many people that do computation in this domain. There are a lot of ideas about how to find vortex crystals with analytical arguments, but this seemed a nice way to really test some of these new ideas. So what we're going to do is we're going to write a point vortex solver which is fully differentiable. So that means if I have a trajectory starting from some initial condition, I can differentiate through that entire thing with respect to the initial conditions. And so we're basically going to try and find all the low energy solutions for specific numbers of vortices by building a loss function. And then I'm going to also try and find homoclinic orbits between these solutions. So this is a very nice paper from 1979. This is kind of held up as the state of the art in this problem. Campbell and Ziff, they considered the problem for a range of vortices ranging up, I think, up to a vortex number of 30, and then a few other cases as well. And you can see here for each number of vortices, they have maybe 4 or 5 exact solutions that they've converged. And the way they converged their solutions is basically they initialized point vortices on a set of rings, and then they did gradient descent on the free energy. And so we're going to try and do something similar. So this is Andrew's code. This is his fully differentiable point vortex solver in a doubly periodic domain. It's doubly periodic because we also want to use it to have a look at some of the high Reynolds number periodic orbits that I've found. I'll show you in a bit later. But now we're going to try and use it for this, this vortex crystal problem. So I'm going to write down a loss function, and the loss function is made up of 2 components. Right? One is the free energy, and that's what I want to minimize. That's what I observe in practice. Another one is a term which actually is looking for relative equilibria. So these are basically the distances between vortices, and this time capital T is my simulation time, and time 0 is my the starting point. And basically, I can take, because this is written in JAX, I can take gradients of this loss function with respect to my initial configuration of vortices. And Andrew does this kind of nice annealing where he starts off with everything on the free energy, so kappa is 1. And then as he does gradient descent, he turns up the relative importance of this term and says you also need to find me a relative equilibria as this kind of goes forward. And he's able to get a very rich set of solutions this way. Now, for very large numbers of vortices, there are lots of states, okay? And often we had missing states. So sometimes we were missing the minimizer. And so what he did in that case was he takes some of his converged solutions and just adds a term to the loss that basically seeks to push the free energy below what he currently has. It's just a sigmoidal term, it's a differentiable function of the free energy, and it tries to push the free energy down. And this really is one of the reasons I wanted to do this problem, because we could build figures like this. Now, if we could build figures like this in the periodic orbit problem, we'd be very, very happy. If you look here at the number of samples, he's able to try 100,000 initial guesses. We don't really have the scope to do that in turbulence. And you're basically looking here at, for various numbers of vortices, I'm showing you the number of samples he's run, the number of states he's converged in blue, and then the number of unique states. And so there's some indication at these low vortex numbers, 10 and 20, that we have hit a plateau. But n equals 30, he also has a calculation at 50. These things are still running, and basically he's nearly getting a unique state every time he runs. These are histograms of the free energy, and basically there is an exponentially large number of states. Increase of all these kind of saddles increase exponentially with the number of vortices, which is perhaps what you'd expect. But right down here, we also get the 1 or 2 states that Campbell and Ziff found. So here are some more of his states, and something happened in this work that I thought was quite exciting that we didn't anticipate. You'll see there are some states here which are shown in red. Now, these states in red, it turns out, are not unique. Right? So these are, if you look at these 3 up here, they are the free energy minimizing solutions for 16 vortices, 18 and 20. They all have this double ring structure. But it turns out that these are actually one of a family, a continuous family of solutions. So there is not a unique minimizer of the free energy for these vortex numbers. There's basically a whole continuous family connected to these solutions with equal free energy. So this is something nice, I guess, about vortex crystals that I don't think was known previously. I'm trying to show you basically what's going on here with this continuous family. So if we just say focus on this 18 vortex configuration, the red crosses are one of these vortex crystals. I can essentially take the outer ring of vortices and move it through this hexagonal shape here. And I remain both on a vortex crystal and the energy minimizing state. So these continuous families of solutions to the Euler equation that are also the free energy minimizing state. And this kind of happened, he noticed this when he was looking, how many unique states have I got? And his criteria kept flagging copies of the same solution. And it turned out they were all members of this same continuous family that he can move smoothly through. So then there's kind of, and this is just showing that in a little more detail. So this is 16 vortex configuration. This is the continuous family. Basically, you move, if I start in the blue cross, I can move all the outer ring to the red cross, and then I reach a permuted copy of the starting state. So then my natural question is, if I'm doing an experiment, which one of this family would I observe in reality? Is there a preferred entry point? If I'm looking for the free energy minimizing pathway between another local minima and the global minimizing state, do I always come in the same way? Is there one state I'd expect to observe? And with AD, automatic differentiation, he's basically able to build these energy minimizing pathways between other nearby centers to this minimizing state. And basically, he finds that there is always the same state. There's a common entry point into this continuous family of solutions, and therefore a state which would most likely be observed if you were doing an experiment. We come down to this state before moving through the continuous family.
Are you familiar with the experiments of Briscoe?
I've read the paper. Yes. Yeah. So I mean, the thing about those experiments is it's beautiful pictures, but it's very hard to look at those pictures and say which equilibrium does this correspond to. You can overlay your equilibrium on top, but it's not going to line up exactly. And so,
because we could do continuous vortex methods on these things, and I could reproduce some of this stuff.
With full Euler equations.
Full Euler.
Oh, nice.
Yeah.
Is that published?
Yeah.
Oh, okay. Yeah, I should look at this.
But it has a weird title.
Okay. So
your fault.
Okay, so the reason that I wanted to look at this problem originally was I also thought it would be a nice place to start trying to find more complex simple invariant solutions. So it's a nice problem to look for homoclinic connections between solutions because the unstable manifolds are very low dimensional and we kind of know that there is an answer to find. But of course we have to worry about the fact that there is a permutation symmetry in this system. I can relabel my vortices, and so that makes it slightly challenging. The way we do it is we basically stick a permutation invariant observable on top of our vortices. So I just put a little Gaussian field around each vortex, and then measuring similarity in terms of this permutation invariant field, it doesn't care about if the vortices get relabeled. And so he's basically able to find homoclinic orbits using this automatic differentiation method where he starts in the unstable subspace of one solution and then runs his solution forward in time, and his loss function basically says, I want to end in the same place. And he's found a bunch of homoclinic connections at various numbers of vortices. This is one in the 30 vortex configuration, and he's just started to look at the Kolmogorov flow, and we've had some early success in that configuration as well. Okay, so I'm going to now, with kind of that simple automatic differentiation problem, I want to go back and look at this turbulent Kolmogorov flow. So this is something we're trying to finish off. We put the paper on archive before Christmas, but our solution numbers have really blown up since then. So this should be submitted in the next couple of weeks if I do some work. And this was joint work with Michael and with Rich, but also some of the software development relied on the help of Peter, who's a software engineer at Google. And so some of the things we've done really kind of leverage that expertise and also the compute power available. So we were able to actually do this on the cloud thanks to this collaboration. So I want to get away from the idea of, I want to find periodic orbits, and I want to find ones that are relevant to high Reynolds number turbulence. And to do that, I'm basically going to have to get rid of the idea of measuring a near occurrence. And the idea really, I think, is linked to something that John Gibson did 15 years ago now, with Predrag actually, and with a PhD student, where he was looking, it was a less than minimal channel, right? So there's a chaotic saddle, but it's kind of a nice starting configuration. And he was looking for unstable equilibria in that configuration. And his approach was that he would just take snapshots from his DNS and plug them into a Newton-Raphson solver. And the rationale was that if he does that, that's kind of a fair sampling of the chaotic attractor. And so the states he finds would somehow be important to the overall chaotic dynamics. Now, we just can't do something like that in high Reynolds number flows for various reasons. I mean, the first thing is you would expect your Newton solve really to ever fail to converge in this case. You're also, and I think this was true in John's work, you're also likely to end up with a solution that's very far from where you started. So it's kind of an admirable approach to look for solutions which are somehow relevant to the chaotic, what you observe in your DNS. But if you plug it into a Newton solve, you're probably going to converge somewhere very far away. And so there's an example here, I think I lifted from Wikipedia, of this phenomenon in a Newton-Raphson solver. This is basically the Newton-Raphson solver looking for the cube roots of unity. And so you're going to converge to one of the three routes, and which one you converge to depends on your starting point. And this is the complex plane colored by the final solution you end up with. And there's this kind of amazing fractal structure. Whereas, so if I just pick an extreme example, if I was to start up in this top right of this figure, I would end up converging, I think, to the solution down here. So your Newton solve tends to converge to somewhere very far away from where you start. And we would like to find solutions that are relevant to what we observe. And so that's where this automatic differentiation approach comes in, and the collaboration with Google is they've written a fully differentiable flow solver that they call JAX-CFD. I don't know if I can move. It says JAX-CFD underneath my face here. And so this was a paper now that I think is very heavily cited since it was published a couple of years ago. The reason that they wanted a fully differentiable solver was that they were training neural networks to learn finite difference stencils. And in order to kind of have stable numerics, they wanted to be able to actually include entire solution trajectories in their training of these neural networks. And so they wrote this thing in JAX. And JAX has all these kind of nice properties, and it has this nice just-in-time compilation feature. It's built on top of XLA, this accelerated linear algebra library, and it can do automatic differentiations. You can get derivatives essentially to machine precision. And it's very, very fast on a GPU. And so we're going to use that solver to do something similar to what I was doing in the vortex crystal problem. I'm going to write down a loss function looking for a periodic orbit. So this part of the loss function here is essentially the norm of what I would find in a Newton solve. This is the time forward map of some initial condition U. Capital T would be the period of the periodic orbit. And then this is some shift in the x direction. If I have a continuous symmetry, I also have to worry about this. So this thing would be exactly 0 for a periodic orbit, and it forms part of my loss function. And then I have, I guess I should call this additional physical terms. So I'm going to actually add terms here that are going to look for periodic orbits that I'm particularly interested in. So you might remember that we didn't really have any solutions that had high dissipation. To account for that, I'm basically going to add a term which is going to look for periodic orbits with a time average dissipation above some threshold d star. So basically, I don't have anything with an average dissipation above 0.15. I'm going to put 0.15 in here and just let this thing go. I'm also kind of interested in the density of states. We didn't really have any short period solutions, so I'm going to add a term to another loss function, which is going to hunt for periodic orbits with a specific period, t star. And I'm basically going to do this a lot of times for various t star, and just kind of carpet bomb this region where we didn't have many solutions before, and see what comes out. So the approach is going to be gradient descent on this loss function through this fully differentiable solver, and then promising guesses are going to go to a Newton-Raphson solver. Now, there's a couple of things in the approach that we kind of stumbled on by accident that work very well, that I don't have a great understanding of, but I still feel it's fair to put them on a slide. The first thing is the importance of the optimizer. So some of the more popular variants of this thing, like an Adam optimizer, they do not work well in this problem. I don't know if it's something about the way these are stochastic gradient descent methods. There's something about the momentum term in Adam that messes this up. We found Adagrad to be highly, highly effective. Basically, Adagrad is doing gradient updates with a feature-dependent learning rate. And so the way that you update individual features depends on the history of their gradients in this normalizing term here. We found that to be highly, highly effective without necessarily understanding exactly why. The other thing is that we're doing all of this in a version of the code which has a finite vertical velocity. And again, this is absolutely key in this flow. We need a flow through the domain, which the optimizer is going to find. So the optimizer is going to allow for a variable flow through the domain, and it's then going to give me a solution which is not a solution to the system I'm interested in. I'm interested in the system with no vertical flow through the domain, but we need to do this basically as a first step to get decent guesses. And so what we would do is we would basically use this as a precondition for going to a Newton solve. If this vertical velocity has jumped up, we might do another optimization where we try explicitly to reduce this once we have a closed loop, and that's quite effective. Basically, any time I can reduce this loss below 0.1, but below 1%, I'm going to take the output and put it in a regular Newton-Raphson solve, which is spectral and does not allow for any vertical velocity. And if you've got a good guess, you'll usually converge something within 10 steps. And so it's kind of an approach which doesn't require a lot of thought, but it's an approach that we can now just let loose on this old problem. So this is a figure I showed much earlier in the talk. These are the known periodic orbits in this configuration that Rich and his postdoc found, and there are 4 of them. And I'm basically going to go back and I'm going to look for periodic orbits with periods every 0.5 time units. And I'm also going to look for high dissipation solutions. And I'm going to overlay on this figure all of the solutions that dropped out of this approach. So I guess the first thing is you'll notice there are lots. There are lots that were missing previously. There are lots and lots of high dissipation solutions. And if you look at where they sit in this kind of production dissipation picture, we are now essentially covering the full range of turbulent events with these short period solutions. So this would kind of call into question some of these assumptions that people have previously had. You know, we don't appear to need long periodic orbits to say something about high dissipation events. Do we need connections to say something about bursting dynamics? Well, we've got lots of high dissipation periodic orbits now that are short. So maybe we need to think again about these questions. And this is a slide I put in really for anyone that's computed periodic orbits in this flow. If you have, you know, when I started, I never had any solutions that looked like this. There are lots of interesting structures in here, right? You can see a little dipole wriggling through here. There are other solutions that look more like vortex crystals with kind of isolated things wiggling about. But we have this kind of huge range of dynamics in these solutions. And if I was to show you a video of a burst, you'd recognize many of these features in the video. Okay, so we have lots of solutions, and we have a reasonable coverage now of the state space. How can we do if we try and predict statistics? So we're not doing periodic orbit theory here. We're doing something data-driven, but what we're doing is kind of inspired by periodic orbit theory. And it's inspired in the following way. So you give me one statistic, and let's say it's a PDF of the dissipation. I want to try and reproduce that PDF from my periodic orbits as a sum over these PDFs of the individual periodic orbits. So this would be a prediction for the DNS PDF. These are PDFs of the periodic orbits, and they're weighted in some way. And I'm going to just learn those weights from data, just in a regression problem, essentially. Then I'm going to fix those weights from this one fitting and try and use them to predict all the other statistics. So the weights will be fixed, and they'll be fixed from a fit just to a single PDF. And the fitting is done by essentially a KL divergence between the ground truth PDF and my one involving the periodic orbits, and then also a constraint that these weights have to sum to 1, essentially. We actually find that in the optimization, the weights never go negative, so we don't have to enforce that explicitly. And so this is how we do. And I probably should have, I did actually show the results from the 2013 paper that had an attempt to reproduce this PDF and this PDF. And these are considerably better, even if perhaps, depending on if you work in real turbulence, maybe these don't look so great, but certainly to us in dynamical systems, this is quite remarkable. This is the dissipation PDF. So this is the one I fit to. You can see now I'm able to kind of capture this high dissipation tail in my periodic orbits. These PDFs and these statistics here are then predicted from the weights just from this one fit. So perhaps unsurprisingly, I do pretty well in the energy production. The kinetic energy, I do okay. There are gaps, and we understand where those gaps are. So we actually know that we need to look for some solutions. For example, we could actually target solutions in this specific region if we wanted. But I think these actually are some of the more moderate length periodic orbits that we did not include do have this region. And so I think we can revisit this quite easily. The really nice thing is, though, when we come to predict the mean profile, it's essentially indistinguishable from the DNS. And even the RMS velocities, there's something like a 3 or 4% error here. Whereas if you look back at the 2013 predictions, the error here was order 100% at least. We just didn't do anything like this. This final thing here is basically how these weights, it's not periodic orbit theory. I haven't computed the weights with periodic orbit theory, but as a kind of rough idea as to whether this is at all similar, these are the weights versus the sum of the unstable flow K exponents. And there's this kind of inverse relationship, which is what you might expect from a periodic orbit theory type approach. So that was all Reynolds 40. And the natural question is, can this possibly work at high Reynolds numbers? And it seems to be working well at a Reynolds number of 100. So this is the case where I think there were 9 solutions known previously. We currently have 144, although that number is accurate as of a couple of weeks ago. That's slightly higher now. And again, we seem to have a kind of full range of very interesting events. So these are some of these periodic orbits. We don't really have enough yet for me to be comfortable to predict statistics, but I'm still showing you some of these solutions here. This is the same way I did before, dissipation versus period. You have this huge number of solutions here, and here they are overlaid on this production dissipation plot against the background DNS PDF. So you have this kind of very dense coverage here. There again, there are gaps. And I think I understand where the gaps, what we need to look for in the gaps, again, comes from slightly longer orbits. But we basically think these are very promising results. The first time we've ever been able to find solutions up in this area without having any rational initial guess, right? My initial guesses were random snapshots from a turbulent flow. I didn't try and set them up in any nice way at all. And so perhaps what we need is some kind of combination of methods. So these are my conclusions, and they really kind of focus on the last part of the talk. We do think we have something now we can use to generate robust guesses for periodic orbits, and we think that we will be able to do reasonable statistical predictions. But I think we need to go a bit further and actually kind of revisit some of the ideas of guess generation in combination with these methods, which might, for example, be using some of our convolutional neural networks to label when we are near to where we started in the state space, without requiring that we have an exact or a near occurrence exactly. So these are kind of open problems that we're working on now. It's maybe not the right room, but I do have a few postdocs and PhD studentships available. So if you know of anyone that's interested in these ideas, then please let them know. So thank you very much. I'll stop for questions.
Any question for Jacob?
Yeah, so on the first part, I missed it at the beginning. So what it was, the encoder I use, I think was in this entitlement in the space. It's not probabilistic.
It's a regular. Yeah, it's not probabilistic. It's just a regular autoencoder. There is no sparsity constraint. This kind of as basic as it gets. Right? So it's a convolutional autoencoder L2 loss. And that's it.
It would be interesting in turbulence when applying similar methods to the usual models and imposing this entitlement, you can get nodes that are more detectable, and that would be interesting.
You say disentanglement, do you mean sparsity?
Yeah.
Okay. Yeah, no, that is something we have thought about actually. So we have this way of finding important directions in that space, but sparsity probably would be.
When you don't do that, then the modes that you have, the latent vectors have
yes.
direction.
Yeah.
But from a physics point of view, what we saw applying that to turbulence is that there is entangled our model. It's interesting moves.
Okay. Yeah. Yes. Yeah, sparsity is something we are thinking about, I think.
Because when you go to turbulent flows, then it becomes more important. And the other question is, when you do the thermodynamics, what do you use?
I'm at no point am I predicting temporal dynamics with no neural networks to predict temporal dynamics. So everything is either like it's a true Navier-Stokes solver, or I'm trying to predict statistics with exact periodic solutions that I have. So there's no temporal prediction in the neural networks.
What I would present tomorrow would be some nice sessions.
Yeah, I have to leave actually, so I'll try and I'll join online and.
Nice presentation.
Thanks.
So just to add, there are many ways of introducing this and finding that in data. But we can talk about today.
I have a cab in 20 minutes, so I'm really sorry. It's kind of a last minute thing, so I'm going to have to run away.
I don't have a question because you find like 140 periodic orbits, right?
Yeah.
How do you know which are important ones to the statistics? Or are they all of them important?
Well, they're all used, so we don't kind of make any pre-selection. At the moment, we use the whole set, and we try and predict statistics, and then you can see which ones are weighted more highly in that prediction. The thing that we're doing at the moment, actually, to try and finish that paper, is essentially take that set of periodic orbits, take a long turbulent trajectory, and use a neural network, one of our better autoencoders, to try and label which solution we are currently closest to. In this kind of Markovian type picture where you're hopping between them. And that would actually answer that question. Which one am I apparently closest to at any instant in time? And then it might be that there are a sparse set of periodic solutions that we need. Certainly can do it at Reynolds 40.
Well, I guess kind of related, you know how things scale, so number of solutions you have to scale to N, for example. I mean,
the number of periodic orbits.
Yeah, sorry.
Yeah, I know. So they're kind of, you know, real. These are open problems, right? There are saddle node bifurcations happening very densely, right? And so I have no idea how a number of solutions. I'd love to be able to do one of those figures like I showed for the vortex crystal problem, where you have like a number of unique solutions and it plateaus, and you can say, oh, actually, I'm confident I have all of them at this solution, but at the moment we don't really have that capability. So I think the best hope is really like some sparse model where you say, I want an important subset of the solutions that holds over a set of Reynolds numbers, and can I build a predictive model with those? That would be the best hope. But there's always the possibility, right, that there are so many saddle nodes and there are important new physics in those saddle nodes that you don't capture at a lower Reynolds number. So maybe, I mean, maybe it's doomed to fail, I don't know, but it's certainly open.
Yes, quite well.
Mm-hmm.
Is that something that's general very hard to make it by just some non-periodic orbits?
So if you, I mean, yeah, so that's kind of interesting. If you just took a set of snapshots and you said, weight them to predict the dissipation PDF, of course you could do this, right? Because, you know, if you had enough snapshots, you would sample all dissipation and then you would do a fit. Now, but then if you took those weights and you said, let's use those exact same weights, predict me another statistic, then I think you would fail. It's actually an interesting control study that we should do, right? You know, I think when it comes to predicting other statistics, I don't imagine that will work at all. That's what this was able to do, yeah. So the weights from a single fit to one statistic were then fixed and then used to sum up the other statistics and make predictions. And so that's what we think is useful.
It seems like you find very simple periodic orbits, but your method actually generalizes more complicated one by the recession kind of orbit or toroidal orbit.
When you say so, when you say they're simple, you mean in this projection they look like little closed loops?
Close up quite nicely.
Yeah. So
some of them have little press.
Yes. Yeah.
But can they actually intersect themselves, or?
So I mean, certainly in this projection, if what's that? Yeah, I mean a torus. So you could concoct a method to find a torus with AD. You could do this. Whether you need them or not is an open question, I think. We're doing quite well with these straight periodic orbits. They look simple in this representation. I mean, certainly if you look at some of the known longer orbits, you'll see them kind of winding back over each other in this picture. But the kind of Citanovich view would be that they are prime cycles glued together. So they're kind of simpler building blocks that are then a longer periodic orbit is constructed from. And again, we could, in principle, use these methods to try and glue solutions together. Yeah, but I don't think there's a restriction of this method to them being nice. Where I do think the restriction comes in is we're very, very good at short periods because the network's quite happy to kind of close a short loop. But if you go for a long orbit, you obviously have sensitive dependence on initial conditions, and you really struggle for the longer orbits. And that's why I think you need some kind of combination of a decent initial guess, and then you go to this.
Before it transforms the orbit,
yes,
you get the fundamental frequencies and higher harmonics. That's a mix of fundamental frequencies plus their mixture of harmonics.
No, so for these things it would be single frequency, yeah, and that would be true even for the long ones you've found, right? There would be a fundamental frequency set by the period.
Or double or triple frequencies that interact. So here you don't find them, or
I mean, these would be tori you're thinking about. Yeah, I mean they are rare, and as far as I know, the ones that have been found in Navier-Stokes have been found in cases where they have kind of emerged as stable attracting solutions in bifurcations. And apart from that, I'm not aware of anyone who's found them. I think you've done some work with Jeremy Parker, right? So he's thinking about these things, right? And we're trying to get him to Edinburgh. Yeah, he thinks these things are important. I don't know. Yeah.
Any final question for Jacob? let's thank Jacob, who needs to catch taxi
Yes.
very early. So, see.
Thank you.